Welcome to Statistics Made Simple. I'm Savita Balsang, and in this video, we will be working out some very important problems based on the Poisson distribution. So let's get started to part 2 of solutions to problems based on the Poisson distribution. In my previous video of part 1 to solutions based on the Poisson distribution, you have come across words like number of deaths, number of accidents, number of mistakes, number of telephone calls received at a telephone exchange, or number of passengers getting in at the first stop, or sometimes in a problem, it was already mentioned that it is a Poisson distribution problem. And I have also mentioned to you that whenever the word defect is used, it is a Poisson distribution problem, whereas if the word defective is used, it is a binomial distribution problem. Since we have already worked out many problems based on the binomial distribution, that is, we have worked out problems very extensively, you will know now how to differentiate between a binomial distribution one and a Poisson distribution problem. Now in this video, I am going to solve 3 problems where the word defective is used. But these problems are very different from what we have worked out under the binomial distribution topic. Now let's recollect and remember a very important property which we learned under the binomial distribution. We had learned a property which is an important 2 marker, that is, under what conditions does a binomial distribution tend to a Poisson distribution. So we learned that there are 3 conditions. First is when the number of trials is very large. That means n tends to infinity. The second condition is when the probability of success is very small. That means p tends to 0. So now, when in a problem, the word defective is used. Please listen very carefully. So when in a problem, the word defective is used, you know that it is a binomial distribution problem. So when it is a binomial distribution problem, what is the next step? You have to identify the 2 parameters, that is n and p. Now, if n is very large, that means even if n crosses the value, say 9 or 10, we assume it to be large. And suppose the probability of success. Remember that probability of success is usually given in terms of percentage, decimals, or fractions. Suppose p is very small. What do we mean by very small? As the number of zeros increase after the decimal, then it is considered to be a very small value. So if these 2 conditions are satisfied, so first look out for the word defective, and if the word defective is used, you know that it's a binomial distribution problem. Next, find out the parameters n and p. And suppose now n is large and p is small. Then the binomial distribution gets converted into the Poisson distribution, and then we use the third condition, that is lambda is equal to np. Now another important point to keep in mind is it's not necessary that both the conditions will be satisfied in a problem. Sometimes both the conditions, that is subdivision A and subdivision B, which you see on the screen, both may be satisfied. But in some of the problems, even if either one of the conditions is satisfied, then the binomial distribution problem will get converted into a Poisson distribution problem. I'd like to repeat myself once again that this is a very important video and is usually a sure 5 marker from the examination point of view. Problem 6. It is known by experience that 2% of articles manufactured by a firm are defective. Articles are supplied in packets of 50 each. First subdivision, what is the probability that a randomly selected packet is free of defective articles? Second subdivision, among 10,000 packets, how many are expected to be free of defective articles? So now in this problem, the word defective is used, and hence you know that it is a binomial distribution problem. So the next step is to identify n and p. Starting with the solution, write given n equal to 50. Then write p equal to 2%. That is the probability of an article being defective. Then 2% you convert it to decimals, which is 2 divided by 100, which is 0.02. Now if you see the second subdivision, they have mentioned 10,000 packets. That means capital N is equal to 10,000. Now let's check the values of N and P once again. Now N is equal to 50 and P is equal to 0.02. What do you see here? We see that N is a large number, that is it is 50, and P is 0.02, which is a very small value. I told you as the number of zeros go on increasing after the decimal, the value becomes smaller. So here you see that the first two conditions are satisfied. That is, n is very large and p is very small. So what happens is that the binomial distribution problem will now get converted into the Poisson distribution. So let's see what are the steps which we have to write. After the given part, the next step you know is to define capital X, that is the number of defective articles. So in terms of notations on the screen you can see I have written that is X follows binomial. Within brackets you have the parameters n and p. In other words, it will be X follows binomial. Within brackets you write 50, 0.02. Now the statement in the next line, which you see in pink color, is an important one. That is your giving your justification why you're converting a binomial distribution to a Poisson distribution. So the statement is, since n is large and p is small, we use Poisson approximation to the binomial distribution. Now the third step is we need to find out what is the parameter lambda for the Poisson distribution. So we'll make use of the third condition. That is, you know that lambda is equal to np. So now you substitute for n and p. So you'll get 50 into 0.02 is equal to 1. In other words, you write X follows capital P. So here capital P stands for the Poisson distribution. Within brackets you write lambda. That means X follows Poisson with parameter lambda as 1. Now that we have obtained the value of lambda as 1, the next step is to write the p.m.f. of the Poisson distribution. So let's remember or recollect that the p.m.f. is p of x equal to, open the flower bracket, in the first row it is e to the power minus lambda, lambda to the power x divided by x factorial, where x takes the value 0, 1, 2, 3, so on. It is infinite, the range. In the next line, write 0 otherwise. Now in this p.m.f. substitute the value of lambda as 1, and hence you will get p of x equal to, open the flower bracket, e to the power minus 1, 1 to the power x divided by x factorial, where x takes the value 0, 1, 2, 3, so on it continues up to infinity, 0 otherwise. Now the first part of the question is that we should find out that the packet is free of defective articles. So always remember, we use the formula probability of capital X equal to small x is equal to small p of x. So in the first subdivision, start with consider probability of capital X equal to 0. What do you mean by capital X equal to 0? The packet is free of defective articles, so which will be equal to small p of 0. What is the next step now? In the p.m.f, wherever you have x, you have to replace it by 0. So you'll get e to the power minus 1, 1 to the power 0 divided by 0 factorial. Then calculate e to the power minus 1 from the scientific calculator. So you'll get 0.3679. And you know that any number to the power 0 is 1. So into 1 divided by 0 factorial is also 1. So the first subdivision answer is 0.3679. Now in the second subdivision, they have asked you to find out the expected number of packets that would be free of defective articles. So you know that whenever they use the word expected, it means we need to find out the expected frequency or the theoretical frequency. And you know that the formula for that is Tx equal to capital N into P of X. So now write the second subdivision sentence as therefore the expected number of packets that would be free of defective articles is, write the formula capital N into P of X, which is 10,000 into 0.3679, which is equal to 3679. Problem 7. A box has 300 pins. On an average, 1% of the pins are defective. Find the probability that the box has first subdivision at least one defective, second subdivision more than 3 defectives. Again, in this problem, the word defective is used. Hence, it will be a binomial distribution problem. So, the two parameters are n and p. In this case, n is 300 and p is 1%. That is the probability of a pin being defective. Starting with the solution, in the given part, we have n equal to 300 and p is equal to 1%, which is 1 divided by 100, which is 0.01. So now you see that this problem, n is large and p is small, and it gets converted from binomial distribution into the Poisson distribution. So the second step is to define capital X as number of defective pins. In terms of notations, you can write that is X follows binomial n comma p, that is X follows binomial 300 comma 0.01. Now write the sentence that since n is large and p is small, we use Poisson approximation to the binomial distribution. Now using the third condition, we need to find out what is lambda. That is, we know that lambda is equal to np, which is 300 into 0.01, which is equal to 3. In other words, x follows Poisson with parameter lambda, or x follows Poisson with parameter 3. So writing the p.m.f for the Poisson distribution with lambda equal to 3, we get p of x equal to, open the flower bracket, e to the power minus 3, 3 to the power x divided by x factorial, where x takes the value 0, 1, 2, 3, so on, 0 otherwise. Now the first part of the question is you should find the probability of getting at least one defective pin. The word at least means greater than or equal to, and in the direct method this would mean x takes the values 1, 2, 3, so on up to infinity. And you know that in this case the probabilities cannot be calculated, so we have to use the formula method. What is the formula method? You start with consider probability of capital X greater than or equal to 1, which is 1 minus probability of x less than 1. Now, which is the value which is less than 1 in the range? It is only 0. So the next step will be 1 minus probability of capital X equal to 0, which is 1 minus P of 0. How do you calculate P of 0? In the p.m.f, wherever you have X, replace it by 0. So you'll get 1 minus e to the power minus 3, 3 to the power 0 by 0 factorial, which is 1 minus e to the power minus 3 will be 0.0498. 3 to the power 0 will be 1 and 0 factorial is 1. So it simplifies to 1 minus 0.0498, which is 0.9502. Or in other words, probability of getting at least one defective pin is 0.9502. In the second subdivision, we should find the probability of getting more than 3 defective pins. So in the direct method, more than 3 means x takes the values 4, 5, 6, so on till infinity, for which the probabilities cannot be calculated. So we have to make use of the formula method. In the formula method, start with consider probability of capital X greater than 3, which is written as 1 minus probability of X less than or equal to 3. Now, what are the values which are less than or equal to 3 in the range? They are 0, 1, 2, 3. So totally 4 probabilities have to be calculated. So the next step reduces to 1 minus, open the square bracket, probability of capital X equal to 0 plus probability of X equal to 1 plus probability of X equal to 2 plus probability of X equal to 3, which is replaced by 1 minus, within brackets you have P of 0 plus P of 1 plus P of 2 plus P of 3. Now P of 0 I have marked it in pink color, whose probability we have already calculated in the first subdivision, and we have got the value as 0.0498. So now the next step reduces to 1 minus, open the square bracket, 0.0498 plus, now to find out P of 1, P of 2, P of 3, what should you do? You have to put X equal to 1, 2 and 3 respectively in the p.m.f. So you will get plus e to the power minus 3, 3 to the power 1 by 1 factorial plus e to the power minus 3, 3 squared by 2 factorial plus e to the power minus 3, 3 cubed divided by 3 factorial, which further simplifies to 1 minus, within square brackets, 0.0498 plus 0.0498 into 3 divided by 1 plus 0.0498 into 9 divided by 2, because 2 factorial is 2, plus 0.0498 into 3 cubed is 27 divided by 3 factorial is 6. So on further simplification, we get the final answer as probability of x greater than 3 as 0.3526, or in other words, the probability of getting more than 3 defective pins is 0.3526. Problem 8. The probability that a razor blade manufactured by a firm is defective is 1 divided by 500. Blades are supplied in packets of 15 each. In a lot of 10,000 packets, how many packets would be, first subdivision, free of defectives? Second subdivision contains exactly one defective. Now again in this problem, the word defective is used, hence it will be a binomial distribution problem, and the two parameters which we have to obtain are n and p. So n will be equal to 15 and the probability of a razor blade being defective is given as 1 by 500, which is equal to p, and I have also given capital N as 10,000. So in the given part, write small n equal to 15, p equal to 1 by 500, which is 0.002, and n is equal to 10,000. The next step is to define capital X as number of defective razor blades. And in the form of notations, you'll write that is capital X follows binomial n comma p, or X follows binomial 15 comma 0.002. Now you see that in this problem n is large and p is small, so we use Poisson approximation to the binomial distribution. And now we make use of the third condition, that is we need to find out the value of lambda using the expression lambda is equal to np, which simplifies to 0.03. In other words, now capital X will follow Poisson distribution with parameter lambda, that is X follows Poisson with parameter 0.03. Now we need to substitute the value of lambda as 0.03 in the general format of the p.m.f. So we get p of x equal to, open the flap bracket, e to the power minus 0.03, 0.03 to the power x divided by x factorial, where x takes values 0, 1, 2, 3, so on. It continues up to infinity, and in the second line write 0 otherwise. Now the first subdivision states that we have to find the probability that it is free of defectives. In other words, we need to find out probability of capital X equal to 0, which will be small p of 0. And how do we get p of 0? In the p.m.f, wherever you have x, replace it by 0. So you'll get e to the power minus 0.03, 0.03 to the power 0 divided by 0 factorial, which is equal to 0.9704. Any number to the power 0 is 1 and 0 factorial is 1. So you'll get probability of capital X equal to 0 as 0.9704. Now in the question, they have asked us to find out the expected number of packets that would be free of defective blades. So because of the word expected, we need to find out the expected frequency or the theoretical frequency, which is got by using the formula capital N into P of X. So substituting in capital N into P of X, you'll get 10,000 into 0.9704, which gives us 9,704. In the second subdivision, we need to find out how many packets will have exactly one defective. So first, we need to find out probability of capital X equal to 1, which is small p of 1. Now in the p.m.f, wherever you have x, replace it by 1. So you'll get e to the power minus 0.03, 0.03 to the power 1 divided by 1 factorial. On simplification, you'll get 0.0291. Therefore, the expected number of packets that would have exactly one defective blade is, so because they have asked the expected number, use the formula capital N into P of X, which is 10,000 into 0.0291, which simplifies to 291. Problem 9. In a Poisson distribution, probability of capital X equal to 2 is equal to 4 times probability of capital X equal to 3. Find probability of capital X equal to 4. So to find a solution to such a kind of problem, we first need to find out the parameter lambda. So start with the equation which is given. Consider probability of capital X equal to 2, which is equal to 4 times probability of X equal to 3, which is nothing but P of 2 is equal to 4 times P of 3. Now all of you are aware that the p.m.f of the Poisson distribution is P of x equal to e to the power minus lambda, lambda to the power x divided by x factorial. So for P of 2 in the p.m.f, replace x by 2, and for P of 3 in the p.m.f, replace x by 3. So if we do that, we get the third step in the solution as e to the power minus lambda, lambda square divided by 2 factorial is equal to 4 into e to the power minus lambda, lambda cubed divided by 3 factorial. You know that 2 factorial is 2 into 1 is 2 and 3 factorial is 3 into 2 into 1, which you get as 6. Now you see that e to the power minus lambda will get cancelled on the left hand side and on the right hand side, and on the left hand side you have lambda square and on the right hand side you have lambda cubed. So lambda square will get cancelled on both the sides and you will be left with only lambda on the right hand side. So please check this step very carefully and understand the calculations which I have explained. Continuing, we get half is equal to 4 by 6 lambda. Now our aim is to find out lambda, so you cross multiply, that is shown in pink color cross arrows. So if we do that, you will get 3 is equal to 4 lambda, or in other words lambda is equal to 3 divided by 4, and if you convert it to decimals you'll get 0.75. Now we need to find out actually probability of capital X equal to 4. So before we find out probability of capital X equal to 4, we need to write the p.m.f. So write down first the general format of the p.m.f or the Poisson distribution. Then in that, wherever you have lambda, you replace it by 0.75. So you will get the p.m.f as p of x equal to, open the flower bracket. In the first row, you will have e to the power minus 0.75, 0.75 to the power x divided by x factorial. And x takes the value 0, 1, 2, 3, so on. And in the second row, you write 0 otherwise. Now we can find out the question which is asked, that is probability of capital X equal to 4. So write, consider probability of capital X equal to 4, which is equal to small p of 4. Now in the p.m.f, wherever you have x, you replace it by 4. So you'll get e to the power minus 0.75, 0.75 to the power 4 divided by 4 factorial, which is equal to 0.4724 into 0.3164 divided by 24. So on further simplification, we get the final answer as 0.0062. Problem 10. In a Poisson distribution, the second probability term is twice the first probability term. Find the mean of the distribution. So let's recollect. In my previous videos, I have already talked about the first probability term, second probability term, and so on. So the second probability term means it is p of 1 and the first probability term will be p of 0. So in the question they have mentioned that the second probability term is twice the first probability term. So write in the given part p of 1 is equal to twice. So you write 2 p of 0. So I repeat again, p of 0 will be the first probability term and p of 1 will be the second probability term. So now again use the p.m.f of the Poisson distribution, p of x equal to e to the power minus lambda, lambda to the power x divided by x factorial. So what is p of 1? In the p.m.f, wherever you have x, replace it by 1, and p of 0 will be wherever you have x in the p.m.f, replace it by 0. So the second step which you see after the given part is e to the power minus lambda, lambda to the power 1 divided by 1 factorial is equal to 2 into e to the power minus lambda, lambda to the power 0 divided by 0 factorial. Now e to the power minus lambda will get cancelled on both the left hand side and the right hand side of the equation. Then on the left hand side you have lambda to the power 1, which is nothing but lambda, and 1 factorial is 1. So on the left hand side you have lambda divided by 1 is equal to, then you have 2, lambda to the power 0 will be 1 and 0 factorial is also 1. So on simplification you see that you will get the value of lambda as 2. Now, what is the question asked? The question asked is you should find out the mean of the distribution. So, we know that the mean of the Poisson distribution is E of x equal to lambda, which is nothing but 2. View and listen to the videos carefully till you understand the concepts and continue to keep practicing till you have understood it well. Thank you for watching, and in my next video I'll complete the Poisson distribution topic by finding solutions to fitting of the Poisson distribution.